Right, we are recording. Does anyone have any questions about any of the problems, any MATLAB difficulties, or anything of that nature?
Is homework due on that soon? I haven't bought mine yet. This afternoon.
Oh, well, the first homework is due on the 30th. Are you gonna be able to do that soon?
Mm-hmm.
Okay.
I just keep forgetting.
Okay.
I just got paid.
Oh, okay, yeah. Well, also that assignment has only 6 problems to it, so you should still be okay. All right. Anybody?
I'll go get something to drink.
Oh, that's fine. Yeah. Okay. Such a quiet bunch you are. So.
I mean,
Does anyone
I'm driving
start-
home. Sure.
Has anyone started the assignment?
Yes, of course.
Okay. And anyone else started the assignment? Okay. All right. Good. All right. Actually, soon, hopefully the next couple days, I'm trying to finish the book to turn into a publisher on Monday. So I'm a bit swamped until then. Another weekend ruined. But hopefully the next couple days I'll be putting up the next quiz. So the first quiz on 3.1 is due tonight. Several of you turned it in today. I haven't graded those yet, but I will very soon. And I allow unlimited attempts. So if you get your score back and it's not a perfect score, 8 out of 8, you can try again. And I'll make a note of which questions you missed. Okay, and then so I'll be sure to keep the quizzes coming. I'll try to get the second homework on section 3.2 posted. For the most part, we're going to have roughly one homework assignment per section and also one quiz per section. Now, some sections we won't spend very much time on. Like we might only spend one class day, so in that case I might combine assignments. But last semester I gave one assignment per chapter, and that would mean like a lot of problems assigned over a span of weeks. And it seems that no matter how big the assignment is, students will always wait until the last few days before it's due. And I'd rather not have that kind of a situation. So, okay, now, so here's where we start to really deviate from what you've seen in an ordinary linear algebra course like 326. So this is section 3.2, the LU decomposition. Okay. So to summarize in words, and I'll call it the 326 approach. Now, those of you who are not undergrads at USM, like most of our grad students, 326 is the number of our first linear algebra course. To solving AX equals B, and I'll even use as much as possible the usual 326 lingo, where you apply row operations to the augmented matrix that is formed by just slapping on B as an extra column to A. So you just do row operations on all of that at once. And then, well, glad you can make it. You haven't missed much. Okay, so you've got augmented matrix. And the objective of that is this row echelon form, which really is just upper triangular. And then you perform back substitution after that. Okay. And that produces the solution x, which happens to be equal to A inverse B, not to do whatever computed that way. Although I guess in 326 you would, because I seem to recall the students there would tell me how they were spending like weeks and weeks about computing the inverse. Like, such lovely, useful skills math majors learn for the real world, huh? Okay. Now, so why would we not do this? What's the problem with this approach? Because certainly there's nothing to stop you from implementing an approach, exactly this approach, in MATLAB. But what works well on paper doesn't always work well in MATLAB, and here's why. There's a couple reasons. First of all, what if we need to solve this system, AX is equal to B, many times with the same A and different B's? Well, what's going to happen is you would be using the exact same row operations all over again. It'd be a waste of work to form the augmented matrix every single time with only this column changing and doing those same row operations. So there'd be a lot of redundant computation, and that's what we want to avoid. We want to make sure that even though computers can perform zillions of operations per second, we want to make sure that there's a need for each one. Okay, so, and the thing is, this sounds like some made-up situation. Mathematicians love to make up situations like this. But it turns out, I swear to God, this one is real. Okay. And we're not really at the point where I can explain to you in a satisfactory way where this comes up. We actually are going to see this later this semester. It has to deal with solving ordinary differential equations that we're going to see this. So that's a few chapters down the road. So this does come up. It's just not some flight of fancy. So that's one problem. The second thing, so really what we're going to do is, if we just go ahead and the row operations only depend on A, as far as which multiple of which row to subtract from which other row, A determines that alone. B does not. B is just coming along for a ride, and it gets hit with the same with all those row operations. So what we'd like to do is only apply them to A, and save them in some convenient way. And so then, when we're solving a different system later with a different B, we can go ahead and apply them to B as many times as we need to. So it's a matter of bookkeeping that we don't want to stick with an augmented matrix. Another problem that actually I'm not going to really cover today, but it will come up on next class, is that you wouldn't be worrying about if you're doing this on paper. We need to try to minimize round-off error. So what can happen is, from all these operations, row operations we're performing, if we're not careful, the error that's inherent in computer arithmetic might amplify substantially as we go from left to right, eliminating elements in all these columns. So the way we use row operations for a computer is somewhat different than how we would use them on paper. For example, row interchanges. Row interchanges are needed much more often when a computer's doing the work and by hand. Okay, so all of this is setting the stage for what we'll learn about today, the LU decomposition. So to come up with a better approach, we're going to step back and look at what we're doing with these row operations from a different point of view. And that point of view is going to be matrix multiplication. Okay. So let's suppose I'm going to make up a situation for performing a row operation. Let's see. I'll make the numbers somewhat interesting. Okay. So let's suppose that this is our matrix. And we want to eliminate subdiagonal entries. So same thing we were doing last time, reducing to upper triangular form. But for this discussion, we're just going to focus on the first column. That'll be enough to make my point. So it's these entries that we're targeting. So from what we saw last time, so if we're going to zero out A21, which is equal to 3, we're going to say that row 2 is equal to itself minus the multiplier, which I referred to last time as M21, because we're eliminating the 2-1 entry, times row 1. Now, what would the multiplier be in this case? Don't remember how we got that. So we want to use this row that has a 5 in this position to eliminate this entry down here. It's a 3. So, what? Okay. One of those is correct. Which one?
What did she say?
It was 5 thirds and 3 fifths.
It's 3 over
3 over 5.
3 over 5. Yes. So because what will happen is we'll take this row, multiply it by 3 fifths, which causes this entry to scale to be a 3, and then subtract it, which will cause a 0 to appear here. All right. Good. Someone remember that. Okay. So now what I'm going to do is, instead of thinking this as just a row operation, we're going to look at this as we're going to multiply A on the left by a certain matrix that will carry out that row operation. And that matrix is called an elementary row matrix that carries out an elementary row operation. I'm not sure why they call them elementary. What?
It's a single element.
Okay. I mean, mathematicians should not go around calling things elementary or basic or obvious, because that just makes people feel bad.
Oh, like the average Russian author who says things are self-evident every third word.
Yeah, things like that. Yeah, or it follows at once. Although I'll bet if you look through my book, you'll find instances of that, and I apologize in advance.
I think obvious is
Yes. So the matrix that we will multiply this by to implement this row operation is actually has a nice simple form to it. So it's going to have 1s on the diagonal. It's going to be lower triangular, so all zeros up above. And then in the position of the entry we're trying to eliminate, the 2-1 entry, is where we put the multiplier, except with a negative sign. So minus 3 fifths. And then zeros everywhere else. Okay. Now, why does that work? The reason why it works is because, so this will cause, because we have every row except the second row is equal to the corresponding row of the identity matrix. The identity matrix, remember, is when you multiply a matrix by to do nothing. It keeps the matrix the same. It's multiplying by 1. It's the identity element for multiplication. So none of the other rows are going to change. But what this is saying is that the second row is going to be equal to itself, so the 1 in the second position, minus 3/5 times the first row. So carrying out a row operation is equivalent to multiplying by an elementary row matrix. So this would give us something where we'd have, well, the first row is not going to change. Actually, no row is going to change, except for the second one. Okay. So then we're going to have a 0 in that position. And then I'm just going to put x's here because I don't care what's here. So I'm going to do that a lot this semester, or this chapter anyway. Okay. Now, in this whole Gaussian elimination process, now that I've eliminated that entry, which one do I go after next?
One.
Yeah, this one. And, okay, so a 3, 1 is equal to 1. So what is the multiplier now? 1/5. So they're all going to be over 5. So now I'll multiply that by another elementary row. Yeah. Okay. So for this one, the second row is a row of identity because we're not touching the second row now, we're touching the third row. And the fourth row is not going to be any different than that of identity. So it's only the third row that's going to have anything interesting. So can anyone tell me what should go in the third row to carry out this operation?
Definitely a negative 1/5.
Where?
I'm gonna say
First column.
first spot.
Yes, it is the first spot because we're getting rid of something in the first column. So minus 1/5. And then, well, what else should be
A
here?
0,
Zero,
and then a 1,
one,
and then a 0.
zero.
Yeah, so 1 over here, because it's the third row that is being modified. So its third row is equal to itself minus 1/5 times the first row. So, and the reason why I'm putting it over here is we apply this operation first, then this one. So we're just going to keep multiplying.
Where'd you get the 1/5 from? I'm sorry.
It's okay. So since this is the entry we want to get rid of, so in general, to get rid of the ij entry, the ij multiplier is the entry you're trying to get rid of divided by the diagonal entry in that same column. So because I'm going to use this row to get rid of it. So what I do is, if I divide by the diagonal entry, this is going to be a 1. And then I multiply by the entry I'm getting rid of, so now they'll equal. So it's the cause of cancellation. Actually, I don't know if you've watched the video from last class, is where I solve the equation and show, oh, here's where the multiplier comes from. Yeah. Okay. So I could keep going to keep multiplying on the left by these elementary row matrices, and eventually I'm going to get to upper triangular form. So, okay. So if I were to write down a description of a whole process, for this case, of a 4x4 matrix, I'm starting with A, and then I'm going to call this matrix M21, M31. The indices are the elements I'm eliminating with that matrix. So I start by eliminating 2, 1, and 3, 1, and then 4, 1. And then I move on to the second column, and I'll eliminate the entry in row 3, column 2, row 4, column 2. And then I have one more entry, this one, in row 4, column 3. And what's left over, after I've done all that, is U, an upper triangular matrix. And I can use this notation now and then for triangular matrices. Instead of writing out the words, it's upper triangular.
Mm-hmm.
I'll use this symbol. So that refers to an upper triangular matrix, and then I'll have a corresponding symbol for a lower triangular matrix. Okay, so this is another view of what Gaussian elimination looks like in terms of matrix multiplication. Okay. And we can infer from these two examples here what the rest of these matrices would look like. But can we get an idea from knowing what each of these individual ones look like, what they all look like when they're multiplied together? That would be a lot more helpful, because what we want to have is a simple record of what row operations were performed during the entire process.
Yeah.
Okay. Now, so what I'm going to do is I'm going to condense these a little bit based on what column they're all operating on. So I'm going to call this M1. The superscript in parentheses indicates these. So that's all the work that's done on the first column. And I'm going to call this one M2. And can everyone see at the bottom of the board? I know it might be harder for some people. I'll get it back. Okay. Okay.
Sure, yeah.
Oh, okay. All right. And then we have M3, which only has one matrix in it. Okay. So now we have M sup 1, M sup 2, M sup 3 all multiplied together with A gives us this upper triangular matrix. And the reason why I'm grouping them together like that is it turns out that these kind of matrices multiplied together, if they're working on the same column, it turns out the product is really easy to express. So now, okay, we had one more entry for this column, the 4-1 entry. So, okay. All right. So, can anyone tell me what is the elementary row matrix for eliminating this entry right here in row 4, column 1? Now,
0, 1, 0, 0, 0.
Negative 2/5.
yeah, minus 2/5. That's the multiplier because
Zero,
it's
zero,
because you're eliminating a 2, but you're having a diagonal entry of a 5. Okay, so now I could say that M1, M sup 1, but one matrix that does all the work in the first column, is a product of these 3 elementary row matrices. Okay, so in this order, so M2-1, M3-1, M4-1. And I won't fill in the zeros, but all the non-zero entries. One's down the diagonal, and then the 3 multipliers. So we had, first one was minus the multipliers, minus 3/5, minus 1/5, minus 2/5. Okay. Now, it turns out that if I were to multiply all those together, that the product is a very simple form. It's a very similar form to each of the 3 that are making it up. One's down the diagonal. All zeros up above. So it's lower triangular again. And the multipliers just stack together in that column. So we have minus 3/5, minus 1/5, minus 2/5. Everything else down here is 0. That's it. And this is something that, if you were to carry out this matrix product, you could convince yourself of. But it is because you have so many zero entries, and you also have these ones along the diagonal, that just works out so nicely that way. Okay.
Question.
Yeah.
Can you continue to do that with columns 2 and 3 and put them on the 1 matrix?
Oh, like down here?
Mm-hmm.
It turns out, unfortunately, not quite, or I should say, not yet.
Okay.
Yeah, it's a really tricky thing, but yeah, you actually are previewing what's going to come. So that was a good question. So, yeah, because ideally, I'd like to be able to say, oh, okay, all the multipliers go in there. That doesn't quite work. But first, before we go any further, I'll talk a little bit about this kind of matrix. So we know it's lower triangular, but there's something more to it, because not only is it lower triangular, there's all ones down the diagonal. So we have a name for that. That is a unit lower triangular matrix. And in fact, I have an abbreviation for that too, because I don't like to write out unit lower triangular. So I use my lower triangular symbol, and I'll put a 1 here. Represents the ones along the diagonal. So that's my shorthand for these kinds of matrices. Okay. Now, so we've seen upper triangular, lower triangular, and now we have unit lower triangular. And it turns out that these kind of matrices have some very useful properties to make them very easy to work with. Okay, so even my own writing just stays on the board somehow. Okay. So this board is just gonna display all math of any kind ever by the time the semester's over.
Well, let's just hope it's good math.
Well, this is. I guess it depends on one's tastes. All right, some people think modern algebra is good math.
Oh.
No one's perfect.
Do you teach that class?
Never. Okay.
I wish you did.
Okay. Let me. I mean, it's out of my
Yeah,
expertise, but I do habitually help students with it,
Right.
especially in the spring, because you have an instructor who's down to coast, so she's not.
I'll be in your office for most of the
Okay.
classes.
Well, it's a tradition every year. I get some people for that class.
It's modern as hell.
Okay. Okay. I do offer similar services for real analysis, by the way. Okay. Now, properties that triangular matrices have. And I'm going to use my shorthand to express them. Okay. So first, if you have a lower triangular matrix times another lower triangular matrix, the product of them is lower triangular. So that's what this crazy sentence says. Lower times lower equals lower. Same thing is true of an upper triangular matrix. You just transpose the whole situation. So upper triangular times upper triangular equals upper triangular. Okay. Now, so multiplication preserves triangularity. And that's something, like you can take the formula for matrix multiplication and convince yourself of that. Okay. Now, second property is that a lower triangular matrix, if it has an inverse, so if it's invertible, you take the inverse of it, that is also lower triangular. And the same is true for upper triangular. All right, but you want to make sure, like, if you look at these, if you're writing this down in your notes, you look at your notes later, it's like, what is this? So make sure you have that straight. And of course, I have to be careful here. If the inverse exists. Now, it's easy to tell if a triangular matrix has an inverse, because you just look at the diagonal entries. They all have to be non-zero. And finally, if we have a unit lower triangular matrix, or two of them, you multiply them together, that is also a unit lower triangular matrix. And we saw an example of that over there. I had 3 unit lower triangular matrices, multiplied them all together, the product turned out to be unit lower triangular. So that's actually something that's true always. And also, if I have a unit lower triangular matrix, it has an inverse because all the diagonal entries are 1. And that inverse is also unit lower triangular. So both those properties are preserved. The triangularity and the ones on a diagonal.
So the first one, it didn't have to be ones as the diagonal.
Right, yeah, so whatever you have on the diagonal,
Those is non-zero.
well, for this, yes, yeah. Well, actually, what will happen is, if I have, whatever I have here on the diagonal, it'll be 1 over that in the inverse. That's why it has to be non-zero. Okay. Now, so now back to these elementary row matrices and products thereof. If I take one of those elementary row matrices, I'll take the one for 1 that has a minus 2/5 sitting down here. I won't bother writing the zeros. Okay, so as an example of this one, it turns out not only do we know from right here the inverse of this is it exists and it's unit lower triangular, I can actually write down what it is very easily. So M for 1 inverse turns out exactly the same except sign change. So the inverse has the actual multiplier in the same spot. Now, from this we get something more. I had 3 matrices like this written over there, and I wrote down what the product was. It just stacked the negative multipliers on top of each other. Well, this is exactly the same structure, just of a different sign. So that is going to work the same way. So I can say that M1 inverse will stack the positive multipliers. So it'll be 3/5, 1/5, 2/5. Okay. All right. So now we know what those look like. Now, one thing I want to emphasize is to get from this to this, I'm not expecting you to see why it worked out that way. It's not something you're going to look at like, oh yeah, of course. So if anyone's doing that, that's just bravado. But it is something where, like, if you took the time to work out the inverse, like you say, well, this times some unknown matrix X equals identity, and you work out what that unknown matrix has to be, then this is what you'll get. And this is something that you can show for any situation, like wherever this multiplier might be in the lower triangle. So I'm not, so this is something I am asking you to take on faith. I mean, it can be shown, we're just not taking the time to do that. As far as showing that once you have these matrices, how these stack on top of each other, that's actually a little easier to show. Again, I have not done that here. I do have a problem in the book. Actually, it's 2 problems where you can actually prove this. that you because now, does anyone remember from linear algebra when you take three matrices and multiply them together? So you have a product of three matrices, but then you take the inverse of that. What can you say about the inverse of a product? Because this is M41, M31, M21, all multiplied together and then taking the inverse. But how would I express this in terms of the individual inverses?
It's the product of the inverse.
Whoops. Okay, say again?
It's a product of the inverse. Like, in other words, it's like M41.
Almost. There's something you have to do, though.
What does
You reverse the order.
In reverse order.
The reverse order, the inverse.
Yeah. So it's M21 inverse, M31 inverse, M41 inverse. Okay. All right. And we know what all of those are. Okay. And it's because we know what these are that it just changes the sign that why all these stack together so nicely. Okay. Now, so why? Now I can finally get to that part. If we see where we were before, we started with A, multiplied by M1 on the left and M2, M3 to work on the first, second, third columns. And we wound up with U. So now that I know something about the inverses of those, I can move them to the other side. So I can say that A is equal to, so I'm going to multiply on the left, first by M3 inverse. So I still have U over here. And then I have M3 inverse. Actually, yeah, I'll leave it that way. M2 inverse, and then M1, whoops, inverse. Okay. And I know what all of those look like, those three inverses there, because they're all unit lower triangular, and they each have their respective multipliers in the appropriate column. So first column, second column, third column. Now I haven't worked out what these two are, only this one. For the other ones, I'd have to continue the Gaussian elimination process and see what those multipliers would be. Okay, well, but I'll go ahead and write out the at least the structure of them. They don't have U as upper triangular. Okay. Well, never mind. I'll put U. Okay. So in this one, we have multipliers. M21, M31, M41. Then over here we have M32, M42, and then over here we have M43. So all the multipliers are sitting there in those individual matrices. Okay. Now, hello. Oh, can you enter your password real quick?
I never tell you what it is. 27 characters. And you're gonna be like, who's that random person that keeps popping up?
Okay. Okay. All right. Now, so this matrix, all three of these. Okay. This product. What do we know about it?
It's going to be a lower triangular matrix.
It's lower triangular. What more do we know? From over here, they're not just lower triangular.
The
Unit.
Unit
Yeah,
lower
and because
triangular.
all three are unit lower triangular, the product is unit lower triangular. So I know this much anyway. Okay. Now, let's get back to the question that Catherine asked earlier. Because you were asking over here, where have I written it? Oh, yeah, that if do the multipliers stack? Like they do over in this case for first column. And if I went ahead and multiplied all of these together, would those multipliers also stack? And the answer over here is no. The answer over here is yes. And the reason why is because of the order in which they're multiplied. Because it's opposite of how it was before. So it turns out that I know exactly what this has. It has all the multipliers stuck below the diagonal. Okay. So in this last corner of this board that I have, I can finally write down, at least it's very short, here's what I've derived for you. That we have this factorization. A is equal to L times U. So this is what Gaussian elimination accomplishes. It doesn't just give you row echelon form so you can solve a system. It actually factors a matrix, A, into a product of a unit lower triangular matrix, L, and an upper triangular matrix, U. Okay. And furthermore, what we know is that U is the row echelon form that you can then feed to back substitution and solve your AX equals B. And L has all the multipliers. In other words, it has a nice, concise record of what was done to A to reduce it to row echelon form. You see all the multipliers right there. You know which rows they were involved with. Because, like for instance, it's N31 here. You know that this number was multiplied by row 1 and subtracted from row 3 by virtue of where it's located in the matrix. So as long as you have that L, then whatever your B is, if you solve the same system AX equals B with a zillion different B's, you know what row operations you need to apply to that B. All right. So this is the matrix decompositional approach to linear algebra. And it was considered so groundbreaking to view matrix operations in this way, as some sort of decomposition like this, that in the year 2000, when people in my field decided to name the top 10 algorithms of the 20th century, this was one of them. Not just LU decomposition, there are many matrix decompositions, and we'll see some of those. But just the whole notion of decomposing matrices into something of a nice form to work with that would then make problems much easier to solve. So it really makes these processes that you saw in 326 a lot more practical. Okay, so first, any questions about what happened here with the manipulations? Now, so carrying out Gaussian elimination implicitly gives you L and U. And now I can explain to you better than I could last time. When I laid out the Gaussian elimination algorithm, I said I wasn't actually going to zero out these entries because it was a waste of time. Well, it is. But it turns out what I would do is, in Gaussian elimination, as you compute these multipliers, you store them in the lower triangular part of the matrix. Everything, the result of your Gaussian elimination is camped in the upper triangular part. So in other words, you're making use of the whole matrix. So from Gaussian elimination, you overwrite your original matrix A with your row echelon form up here, multipliers down here. So now that we have all that information, I'll explain to you, here's how we can go ahead and solve AX equals B using the LU decomposition, also known as the LU factorization.
I have another question.
Yeah.
When you do end up stacking them
Yeah.
at the end, is it going to be the positives or will it be the?
Oh, in other words, when you do that formula for multipliers, aij over ajj, it's exactly that. There's no negation in here. Yeah, the original elementary row matrices have a minus, but because what's going on over here are the inversions of them, that takes away the minus. Okay. Now, okay, so how to solve AX equals B given this decomposition? A is equal to LU. So it turns out there's actually not very much to it. Because what you do is, in the equation AX equals B, I'll just replace A with LU. LU X is equal to B. Now, so this vector in here, so X is a vector, so U times X is also a vector.
Yeah.
So I'm going to name that vector Y. So we don't know what Y is yet because we don't know what X is either. But what we do know about Y is L times Y is equal to B. And then we have U times X is equal to Y. So what I've shown you here is that the original system that we have, AX equals B, which can be a real pain to solve for a general matrix A, by performing Gaussian elimination, we've broken that difficult system down into two simple systems to solve. And they're simple because both the matrices involved are triangular. Now, it took a lot of work to get L and U, but now that we have, then it's smooth sailing the rest of the way. So I'll write down the process. So first you perform Gaussian elimination. Which produces the LU decomposition. A is equal to LU. Okay. And then, now this is pretty expensive. This takes order n cubed flops or floating point operations. So pretty expensive. We want to do that as rarely as possible. And then we solve this system, Ly is equal to B. Now L is lower triangular, so what method do we use to solve that? No. Forward substitution. Okay. And let's see, give myself a little more room here. Okay. Now the algorithm for that, not very much. Well, it's similar to the algorithm you've already seen for back substitution. So you loop over all the equations from 1 to n, but so in order from the top down, and then you set your unknown, each element of y equal to the corresponding element of b to start with, and then you're taking terms from the lower triangle of L and moving them to the other side. So you need another loop for that. Now, back substitution had a loop that went from j equals I plus 1 up to n. But this is the opposite. It's all entries less than I because it's lower triangular instead of upper. And so then we subtract off terms corresponding to elements of y that we already know. And then, that's actually it. In back substitution, we had one more step. We would take our unknown and divide it by a diagonal entry. And how come we do not need that here? What do we know about L in its diagonal entries? They're all equal to 1. So for a general lower triangular matrix, we would need to have a division here. But in this case, with L, we don't. Okay. So you can compare this to the back substitution algorithm and see how, in every respect, they're opposites of each other. And if you were to step through solving a sample lower triangular system, you would see where this algorithm comes from. And this requires a lot less work, order n squared, floating point operations. It's actually n squared minus n, because back substitution requires exactly n squared. Here you don't need a division, so that's n less. Okay. Now, before I go to the last step, this is equivalent to what you used to do with the augmented matrix. This has the effect of applying the row operations to B. Now, last time I actually included that in the Gaussian elimination algorithm. Now we actually don't include that anymore. It's done here. Because, and the reason why this makes sense is, what do you do to reduce A to upper triangular form? Effectively, you're multiplying by L inverse. How am I getting the modified B? I'm multiplying by B by L inverse. So it's all the same process. Okay, so all this means is before with augmented matrix, you do the row operations on A and B together. Now we've separated those pieces. And finally, we solve U times X is equal to Y using what?
Back substitution.
Yeah.
Back substitution.
Yeah, you're on the right track of upper triangular. Yeah. So yeah, the method we use for that, back substitution, and that uses order n squared floating point operations also. Okay, so now that we are able to solve a single system X equals B, suppose you have a new system with the same matrix A, but a different B. Well, in that case, so if you get a new B, just repeat steps 2 and 3, the cheaper steps, using the same LU that you already have. So that'll save you a lot of work if the need to solve many systems with different right-hand sides arises, which actually, as I mentioned, does happen in applications. All right. So now we have a much more economical way of solving system equations that avoids redundant operations. Okay. Is there any questions about this three-stage process? Okay. Oh, I have 18 minutes left. Okay. Now, so in fact, one of the problems from a section is implementing, from this chapter, is implementing your own routine for solving A equals B that carries out all these operations, because you'll already have a function from the first homework that implements back substitution. Also, another one from the first homework that implements Gaussian elimination. Forward substitution will come later, and you'll just put all the pieces together into one function that will do all of that. Okay. Now, Okay, now I want to say a quick word about, since I mentioned you can be writing your own function and solve a system of equations, but to use in MATLAB, but how do you solve systems in MATLAB using functionality that they already have? So, and it's actually very easy. MATLAB provides an operator for this purpose. X is equal to a backslash b. And so just as a forward slash is used for ordinary division, the backward slash means whatever's on the left of the backslash, you multiply the item on the right by its inverse. So this has the same meaning as A inverse B. Whereas if you have like A forward slash B, so that's the same as A B inverse. So the item on the right is inverted. Now, if you just have numbers on both sides, it's just plain old division. But if B is a matrix, then it's going to compute the inverse of that matrix and perform the operation if it's something that actually makes sense. And actually, as graduate students, we claim that the solution of AX equals B simply is A backslash B, and that all the numerical methods they were trying to teach us were just propaganda. So this is something that you can use to, like for instance, if you're writing something that's to solve system equations, you can use that to check your work. Now, as a result of helping people with the problems on the first homework, I want to mention a few other MATLAB functions that you might find useful. So to create matrices and also vectors to test with. So for instance, one of our problems is writing a back substitution routine that works on an upper triangular matrix. So what you want to do is create a system to solve using backslash to get the exact result, and then try your function on it to and make sure that the result agrees. So for instance, if I want to create a random matrix, so you could do something like this, where m is the number of rows and n is the number of columns. So that'll create a random matrix. All the entries are distributed between 0 and 1, uniformly distributed. And if you want a square matrix, number of rows and columns are the same. You can just pass one argument and it'll do that. And similarly, for a vector, now you want, like for solving AX equals B, you want B to be a column vector. So I would pass in like however many rows you want, and then just one column. And that gives you a column vector, which is, for the most part, column vectors are what we'll work with. If you swap these, it would give you a row vector. Now, sometimes you want a random matrix that has a certain structure to it, like you want a random upper triangular matrix. So there's function. So once you have a random matrix in general, what you can do is, if I do something like this, try U, so TRIUA. What that does is it extracts the upper triangular part. So this is something you can do. Like if A is a random matrix, then this will give you a random upper triangular matrix. Similarly, there's try L, that's an L, for to get a lower triangular matrix. Okay. Let's see. All right, other functions that you will find useful. Suppose, okay, if you're writing a function that takes as input matrix or vector, and you need to know the dimensions of a matrix or vector. So if I do this, square bracket mn square bracket is equal to the size of A, where A is any matrix. Okay. Then M will hold the number of rows in A, and this N will be the number of columns. So, because for instance, in say Gaussian elimination or back substitution, they have for loops that are going like from 1 to n. We got to know what n is, and this is how you get n. Also, for a vector, whether it's a row or column vector, it doesn't matter. You can do n is equal to length b, and that gives you the number of elements in the vector. Okay. All right, so these things I'm telling you here are meant to help you close the gap between, like for instance, you have the algorithms in the book, and now you need to implement them in MATLAB. So a good starting point is like literally copying from a PDF and pasting into MATLAB, and then fixing up the syntax so that it conforms to MATLAB syntax. But then you also need to use things like this to complete the picture. And then also these to set up appropriate test cases to make sure you're really solving the same thing, comparing to the right answer. Okay. Let's see. I think actually, for most part, these will get you through the assignments of problems in the first homework. Okay. All right, all right. Does anyone have any MATLAB questions at this point?
How do we submit that to you, our homework?
Ah, yes, very good question indeed. Okay. All right, so what I want to see in homework, and it's best to just submit the thing by email. If there's anything that's written out on paper, you can just send pictures of that. So I want to see any M files that you made, for whatever functions, or also any scripts. Definitely send those. Also, a diary of your MATLAB session in which you use those files. So in other words, I want to see your code, and I want to see your output. So what I would suggest is, at the prompt, when you're going to start running your code to produce results to turn into me, at the prompt you do diary, and as an example, let's make a file name like homework1.txt. The .txt extension is important because then it's easy for me to open up in a text editor and then look at what you did. So then you go ahead and do all your stuff, and then you do diary off at the end to close it. Or if you just quit MATLAB, that would have the same effect. Also, for diaries, if you go ahead and create a diary, run some of your stuff, then come back to it later and do diary again, that works. In other words, it won't wipe out what you did before. It'll tack it on the end.
So we just email it to you?
Yes. So that's what I got last semester. I got emails with a bunch of attachments and so forth. Okay. For any problems that are not really MATLAB in nature, something worked out more on paper, the best thing to do is, you suppose you take pictures of what you do on paper. I would prefer that you put all that in a document, like a Word document or something, or if you can generate a PDF from whatever you like that. It's kind of a pain when I have a whole bunch of individual files, like one for each page, because my email program takes forever to load them, and it seems to want to load them many times. And no, I don't use Outlook. I will never touch that thing. I mean, I'm using the same old USM email as you guys, but no, I will not use Outlook. So that again, I'm not saying absolutely have to, but it's something that makes the grading process a little less aggravating. And of course, you want me in a good mood when I'm grading your homework. So, one thing that was done last semester is like sometimes someone would turn in anything else done on paper, like actually turn it in to me in person and then email me or stuff later. I'd actually prefer not to do that because then I like to have everything in one place. Because then I can just grade it all at once. So what will happen is so once I grade it, I'll respond to your email and saying, here's your score, here's where you lost points, and so forth. So then we can make sure that there were no mistakes or that nothing was overlooked. Okay. Any other questions about homework submission? Okay. So what I thought about doing for the last few minutes was also pointing out how the LU decomposition, like one problem that you would have definitely worked out in your first linear algebra course was computing the determinant of a matrix. And it turns out that the determinant of A is equal, determinant of a product is a product of determinants. But the product of the determinant of a triangular matrix is all the diagonal entries multiplied together. So the determinant of L is equal to 1. So it's actually just the determinant of U. All the formulas they teach you in your first linear algebra course are way too expensive. They take like a factorial number of operations. It's awful. The fastest way to compute a determinant is just go ahead and carry out Gaussian elimination, get your row echelon form or your U, and just multiply its diagonal entries together. So the total amount of work is order n cubed. But actually, in the numerical linear algebra world, we don't really care about determinants that much. They don't really give us the information we need. Like a matrix is invertible if and only if its determinant is non-zero, but it's actually not the best indication of invertibility that we have. Okay, so the only thing that I haven't got to, which wasn't part of the plan today anyway, is what happens to this process I showed you of computing this LU decomposition in a case where you're going for Gaussian elimination and you must carry out a row interchange or else divide by 0. How do row interchanges mess with all this? So that is what I'm going to cover on Tuesday. So if you haven't gotten the first quiz in yet, please do. And then let me know if any issues with the homework problems, since those are going to be due next class. So, over and out. And wow, another smooth recording.